our today's session, let me learn about one of the sequential circuit, which is counter. So, under your sequential circuit, counters comes under your one of the sequential circuit. We have many classification in your counter circuit. Before we are going to that counter session, so let me learn about what are their applications in real time. So, in your industrial and automation, so manufacturing units, so to count your number of objects which are comes out from your production, as well as in your batch processing, how many quantities that can produced on each hour based or your day based. So and based on that we can proceed with your next budget plans. So in your traffic management, so like giving the traffic signals or counting your number of vehicles which are passed on that road, so or giving that signals to that pedestrians. Next, so we have so many applications like in your aircrafts. So we're going to use these counters as to fire that missiles so on a down sequence of counter or up sequence of your counter. So next we are also using that in your health care units, like monitoring your heart rate or missing any pulses, or finding the number of white blood cells in your blood test. So these are your some of the applications of your counter. So as you can also use this counter to create a digital timer. So in your sports or gaming and entertainment applications, so we're going to wherever it is required the time based games. So there also we want to use these counters. So these counters functionality is counting your number of given process. So how many times it is occurred, or a particular event, how many times it is occurred. So and it will give the relation between those inputs and outputs using your clock signal. So a digital counter will be constructed using your flip flops like your register, where each flip flop can hold one bit of data. Now, based on their functionality or how it is controlled, their outputs, so are they controlled with the external signals or not? So based on that, we have two classification on their counters, which are asynchronous and synchronous counter. Asynchronous counters is also called as your ripple counter, where it changes its state of the outputs based on your applied clock signal, or it will based on your applied clock signal it will divide the frequency. So then you can obtain your outputs of your counter, so that it will be your asynchronous counter. And in synchronous counter, all the flip flops, all the states of your flip flops are controlled by a common clock signal or a single clock signal. Another type of counter which is based on your modulus. So how many number of states it can generate, based on that also we can classify your counters into decade counters, so which can give you only 10 states like your decimal number system. So 0 to 9 only it will count. After that again we will have your that decimal counting, which is 1 0 will start. So or your in special applications we're going to use your gray code. So or in we can also construct in all the time we can require your up counter or a down counter. So we can also design your, so only using one control signal, so we can design the up counter or your down counter. And registers must be converted into a counter by connecting your output of your registers as the input again. So you can also construct your ring counters. So in such applications, so these are the in such applications, so these many different counters are used in suitable applications. So now let me learn about asynchronous counter. In this asynchronous counters, so we can use the GK flip-flop, which is operating under your toggle mode, or you can also use your any type of flip-flop, but they should function like a toggle. because our binary sequence, let we write here as the binary sequence of a 3-bit or 2-bit is started with 0 0. Next one is 0 1. So next one is 1 0. Then 1 1. So by just observing the first bit position, so the initial state is having 0. Next state is having the least significant bit is 1. And the third stage is having your least significant bit is 0. And the last stage is having logical 1. So upon after every 1 bit your state of the flip-flop is toggling. So initially we have 0, then 1, then again 0 as well as 1. So the input clock signal frequency must be divided. That would generate your low counter or low flip-flop outputs. So here the second bit while I'm observing, so for every 2 states your outputs are changing. So such type of design we have to follow here. So as since here lowest significant bit is altered for every clock signal, so we're going to use the toggling state. So where the toggling state is available in only JK flip-flop or in your toggle flip-flop. Hence to construct your asynchronous counter, so we are going to use the ripple counter. We are going to use your toggle flip-flop or any type of flip-flops you can prefer. So that can function like a toggle flip-flop. So those only suitable to design your ripple counter or your asynchronous counter. Now here I took to design your 2-bit asynchronous counter where each flip-flop can hold 1 bit of data. Hence I'm going to use your 2 flip-flops which are in toggle mode. So in your JK flip-flop, so toggle state is achieved when J and K inputs are equal to high. So hence JK inputs are started and given to the high state. So J and K become logical 1. It always gives your output which is a toggle state of your previous output. Now, so here in your asynchronous counter, you need to connect your clock signal only for the lowest significant flip-flop, and the clock for the second flip-flop will be the output of your lowest significant flip-flop must be connected. So here I used your negative going edge triggered flip-flops. So in this negative going edge triggered flip-flop, so the state of the flip-flops can change only on your trailing edge or your falling edge of your clock pulse. So now at this falling edge of your clock pulse, the state of the flip-flops will change. So now here clock is applied only for the lowest significant flip-flop, which is your Q0. Here Q0 is your least significant bit and your Q1 is your most significant bit. So here I need to construct a 2-bit counter, up counter. Hence I used a negative edge triggering along with your 2 flip-flops which are operated under toggle flip-flop. Now initially using your asynchronous input, so let me clear your flip-flop states. So using the asynchronous input clear, so we can clear that. So by just connecting all the clear inputs together, so clear your flip-flop with 0. So by enabling clear bar with a 0. So now clear bar clear if you transfer 0, 0 bar is equal to logic 1. So hence this outputs will give you the logical 0 output. So hence here we have your outputs which are Q0 and Q1 initially are at 0 state. Whenever the first clock pulse negative edge comes as your input of your least significant flip-flop Q0. So my present state is 0. So since the toggle input JK inputs are 1 1, so your present state must change its state to the toggle state which is logical 1. Hence, so there is a rising edge at your output of your first flip-flop or the least significant bit, and this state is continued till you get your next negative edge. So hence this logical 1 state is continued till we get your second clock pulse negative edge. Upon getting that negative edge of your second clock pulse, so here your output will toggle from present state of 1 to the next state of 0, since my JK inputs are 0, 0. Hence I obtain a 0 state. Next, this is continued till you get your third clock pulse. So like this, so for every 2 cycles of your input, so your output will have your least significant bit will only generate 1 clock cycle. So now the frequency is divided by 2 from your clock signal at your output of your least significant bit. Now here the least significant bit flip-flop is having a clock which is from your Q naught. So now this Q naught is applied as your negative edge triggered clock. So when it is equal to, when that output of your Q naught is falling, then it will changes its state from present state to the next state on your second flip-flop. So now initially, so trailing edge comes at here after the 2 cycles of your clock signal on your least significant bit. So hence previous state whatever is there. So since our clock input is at high state, not at your trailing edge, so it continues your previous state as your next state up to the 2 clock cycles. Upon having your Q naught, when it is having a falling edge, then from your present state, so since my JK inputs are 1, 1, so it has to raise to the logical 1, and this state is continued on your Q naught up to the second negative edge. So like this, so you have your toggle state from your 0 to 1 when your negative edges comes at your input of your JK flip-flop or second flip-flop from your output of your first flip-flop or your least significant bit. So now by observing here, so on your first clock edge, so your initially when it is resetted, you obtain your 0, 0 state, and next, so on your falling edge of your first clock pulse, your Q1 is having a state of 0, Q2 is having a state, Q0 is having a state of 1. So on your third clock pulse, so Q1 is shifted to 1, your Q0 is shifted to 0. On your fourth clock pulse, you have your logical 1. Now just by observing this successive states, so here we have a difference between these successive states is logical 1, hence it comes under your up counter. Now to design your down counter, so we have to use, instead of connecting your previous state Q1, we have to connect that complementary state of your least significant as your clock signal. Now if I connect your clock signal like this, so we can obtain your the design of your 2-bit triple counter. So it will start with your 0 sequence is the initial cleared output of your flip counter, and next state will be the maximum state of your counter, which is 3, then 2, so which is decremented by 1 from your successive successive states, which are 1, 0 and 0, 1. Then after 0, 0, after 0, 0 again the sequence repeats with 1, 1, then 1, 0, like this. It keeps on having a sequence of down, so down sequence. So when I observe that difference, so your previous states are and previous state and your present state will have your only one is the difference, so which is lesser than that of your previous states. Your next states are one less than that of your previous states, hence it is known as your down counter. Now since like your previous up counter, here also we are going to apply here J and K are with logic 1, JB and KB are also is applied with a logical 1. Instead of connecting Q1 as your clock signal, here we need to connect your complemented least significant bit state as your clock to the second flip. Now hence in your timing diagram we mentioned your Q1. So Q1 will toggle for every two, it will give you the toggle for every after one clock cycle of your input signal. So initially when it is 0, so after one clock cycle it is shifted to 1. After your second clock cycle again it shifted back to the 0. So now we calculated the complemented and uncomplemented outputs on your least significant bit. Now since this complemented output will become your clock for the second flip-flop. So initial state is 0 upon getting your Q1 bar is falling edge. So since it's a negative edge, so when it is having a negative edge, so this 0 is shifted to logical 1, and until unless you get your next negative edge on your Q1 bar or your complementary state of your least significant bit, so the state will be continued. So next whenever you get the negative edge on your complementary state of your least significant, then the state will turn from your logical 1 state to the logical 0. Since our JPKB is also at logical 1 state, so which is acting like a toggle state. Now by observing this timing diagram, initial states on your Q2 is 0 and Q1 is 0. So Q2 is 1, and then next state in your down sequence is 1. Q1 is 1. So after 1 1, so next state must be equal to the 1 less than from your previous state. So 3 minus 1, which will be 2. So Q2 is 1, Q0 is least significant, which is 1 0. Next subsequent state after 1 0 is 0 1, 1 less than that of your present state, which is 0 1, and subsequent of your 0 1 will be your 0 0. Upon getting 0 0, again the sequence which comes from your maximum count sequence, which is 1 1 to the 0 0. Like this count sequence is repeated based on your continuous clock signal which you are applying on your least significant flip-flop of your 2-bit ripple counter. So we are calling this ripple counter or asynchronous counter since the least significant bit will will do the division of your frequency of clock by 2, whereas your second flip-flop will divide the clock frequency with the division of 4. So now like in your ocean, like how the ripples will come in the same manner here, when it comes to shore the ripple strength will be less when it is on your when it comes to shore the ripple strength will be more, and when it is on that sea the ripple strength will be lesser. So in the same manner here, so for every so at your least significant bit, so here it is divided by 2 on your least significant. When it is coming to the next most, so it is divided by 4. The frequency is divided by 4 by the clock signal in the down counter. Hence it is named as your ripple counter. So in next class, our ripple down counter. In next class we are going to learn about your 3-bit asynchronous or your ripple counter up and down counter.